at the Kennedy Space Center in Florida.
4, 3, 2, 1. We have SRB ignition and liftoff. Liftoff of mission 51D and the 7-member crew of Discovery, and the shuttle has cleared the tower.
Its mission? Nothing out of the ordinary. To deploy 2 communication satellites. But this was the beginning of one of the most important episodes in the history of the manned space program, with the failure and ultimate in-orbit salvage of a communication satellite. This is the story of how NASA, Hughes Aircraft Company and its subsidiary Hughes Communications, and their insurance underwriters worked together, overcame incredible odds, and turned tragedy to triumph. Saturday, April 13th. The Discovery crew prepares for the deployment of Leasat F3, also known as SYNCOM. This is to be the third of 4 satellites in the Leasat series, so named because the satellites are owned by Hughes Communications and the services are leased exclusively to the U.S. Navy. Using a unique deployment technique resembling the tossing of a frisbee, F3, like its 2 predecessors, is routinely released from the shuttle's cargo bay.
It's going, guys, and we're taking pictures.
Outstanding. 2 for 2.
But this satellite fails to activate. Leasat F3 is in trouble.
Houston, this is Discovery. We are watching the SYNCOM. The Omni antenna is still down.
The belief is that Leasat's separation lever, its main power switch, must not have fully opened. A crash effort begins to devise a method for opening it. A fly-swatter-like device, developed by ground control and the Discovery crew, is constructed from materials already on board the shuttle. Wednesday, April 17th. The fly-swatter verifies that the lever was fully open all along. The problem with Leasat F3 is far more serious than had been suspected.
Discovery Houston, the window is closed. Perform the set maneuver.
There was nothing more that could be done on this mission. This shuttle crew would return to Earth, minus the happy ending they had sought.
It was an absolutely devastating experience. We aren't used to losing here. We're used to winning, and perhaps we've been a little spoiled by success over a very long time, but I think each of us was trying to cope with defeat.
Leasat F3, drifting in a useless low Earth orbit and unable to get to geosynchronous orbit, is declared to be a total loss by Hughes officials. The future disposition of the spacecraft would now rest in the hands of the group of American and European underwriters who provide the insurance coverage. However, the saga of Leasat F3 was not over yet. It is mid-morning of the 17th, only a few hours after the fly-swatter attempt. The Hughes team, still at Johnson Space Center in Houston, sits down to breakfast.
It was at that point that interesting things started to happen. We were down eating, and we were approached by the commander of the flight that was going to take up F4 in August, Joe Engel. Came over to our table and gave us his condolences and told us how sorry he felt with what had happened on F3. And he wondered about the possibility of recovering F3 like we had done in West Arpalapa.
He thought it was probably easier to stop the spin of the Leasat than we perhaps thought, and it could be done just by a tethered man rather than a free-flying man maneuvering unit. He had a lot of interesting ideas.
Boy, they really looked down, as you can imagine. They were very, very disappointed. I suggested to Chuck and Al that we get together right there that day, because in fact they were going to head back to Los Angeles that day. So I guess it wasn't more than a couple hours after that we had our first meeting on SYNCOM 3.
He also introduced us to some of his crew, Dick Covey, the pilot, Bill Fisher, the physician astronaut, and told us about Ox Van Hoften, wasn't at this meeting, but he said he was a big guy and he was sure he could stop the Leasat just with his hands. It was all very exciting for us. It kind of pepped us up a little thinking about it.
If successful, the mission would be beneficial to Hughes, NASA, and the underwriters. But it would be a mission fraught with uncertainties due to the inability of ground controllers to communicate with the spacecraft. And at this early date, there is no indication that the underwriters, who would have to request and fund a recovery mission, are even interested. But Engel's enthusiasm and desire to try cannot be dampened.
And I think without the intense desire and push that was there from the onset, that quite frankly, I don't think we would have been able to pull it off.
Besides the combined experience of his crew, Engel points out that after the deployment of Leasat F4, they will have an empty cradle, perfect for holding F3. The recovery seems a natural. Engel's enthusiasm is shared by the Hughes contingent. But is a recovery technically possible? Back in El Segundo, the intense investigation to determine the exact cause for the failure continues.
The conclusion that we reached was that it was most likely two switches inside of the spacecraft, okay, not easily accessible, that probably did not activate. There was no way at that time to prove it, and even to this day, we cannot 100% positively prove it.
As the idea of recovery is fully explored, the initial enthusiasm is dampened as potential problems emerge.
At that point, our concern was twofold. Would the propellants have been exposed to sufficiently cold temperatures that they might have frozen, and was the solid motor likely to have been subjected to sufficiently cold temperatures that it might have irreversibly cracked and then failed on ignition?
The problem was that the Leasat F3 was completely uncontrollable. We had no command access to it. That was one of the things the sequencer was going to start. And as a result of that, we could not adjust its attitude. It would be exposed as a result of improper attitudes relative to the sun to extremely cold temperatures, which in turn we felt could cause freezing in the fuel lines, which would be a real hazard. The subsequent thawing might rupture the lines, and we did not want to bring down put a spacecraft in the shuttle bay that would be leaking bipropellant fluids all over the bay.
The hazards to the astronauts from the propellants are the fact that these propellants are very detrimental to people's lungs. They can get into their systems and cause severe problems.
We couldn't think of any way around that, and we were pretty sad, glum at this prospect.
With recovery out of the question, it appears there is no other known way for the underwriters to recoup their loss on F3. But the engineers refuse to give up. Rising to the technical challenge, they begin to consider new ways to create a salvage value for the underwriters. Options which are unprecedented and risky at best, but technically possible.
So rather than give up, we said, well, maybe there's a better way. Maybe instead of bringing it down, it might be possible to repair it in orbit. Let's go take a look at the F4 and F5 spacecraft and see what might be involved in wiring around whatever might have failed. That was the beginning of the thoughts for a salvage mission as opposed to a rescue mission.
Eager to present the salvage option to NASA and ultimately to the underwriters, the engineers developed two possible ideas for activating the failed switches. Thursday, April 25th. Several of the astronauts and other NASA personnel come to El Segundo for a formal yet still unofficial meeting.
I remember the first plan they presented to us was this thing of going in and cutting in through the shield around the rocket motor in the bottom of the satellite, you know, and our eyes got that big saying, we're going to cut through this metal here? No, I don't think so. But the second idea looked like something that we thought really could work.
It was basically the use of the bypass unit that would bolt on the outside of the spacecraft and plug into existing test connections and wouldn't require any difficult hardware maneuvers.
The concept of a salvage mission is born. Yet despite the efforts of Hughes and NASA, all discussions to this point have been unofficial. A salvage mission will still proceed only at the request of and with funding from the Leasat insurance underwriters.
There is a little bit synonymous to what happens when the insurance companies pay off on a ship, is that when they pay the owners for the ship, now the underwriters now have the decision to make as to what they do with the ship. They had the decision to make as to what to do with the spacecraft. So while technically we were beginning to get ideas, we couldn't really proceed until such time as we had an agreement.
Clearly, the decision is up to the underwriters. They hold the key to mission salvage. While the engineers have been moving forward with their salvage discussion, the Hughes legal and financial management team has been pursuing the nearly $85 million total loss claim on the Leasat insurance. Payment of that claim and additional funding from the underwriters for a salvage mission is crucial for Hughes' continued involvement.
We were faced with a situation that, since it was a total loss, unless there were technical steps taken to try to salvage it, it had zero value to the underwriters. And that really was the beginning of our trying to formulate from the legal and the business side what was called the salvage mission, to try to summarize some of the activities that the technical people were putting forward, that they were exploring to try to determine the feasibility for creating a value. Because at that point it had no value, was a total loss. And there would be no revenues for the underwriters to benefit from unless additional steps were taken.
Wednesday, May 8th. A contingent from Hughes heads to New York to present the option of a salvage mission to the American underwriters.
So in the group that went over there from Hughes, there was Bill McGillivray, who is corporate. He's the vice president, treasurer. Pat Jordan, who was the leader of the team and took the lead in the negotiations. Jennifer Smoker, who was the legal presence, and myself for technical.
We really had gone with the idea of suggesting to them, hey, you know, the total loss has occurred. We have some ideas that are unproven, technically risky, but may recoup some money for you. There's an opportunity, whereas right now they were looking into a total loss.
We said that we were by no means assured of success, that it was a daring thing that had never been attempted before, but if we were successful, then they naturally would share with us. And what we sought was simply to cover the expenses that were involved, of which they would be the beneficiary.
What we met when we started our negotiations was total resistance to the concept of the underwriting community funding the salvage mission. We really were taken aback a bit by that.
Not only do the underwriters refuse to fund the salvage mission, some claim that the satellite is not a total loss.
At the point of, you know, when the spacecraft was non-functional, it was a total loss, obviously a total loss. And even at the beginning of the start of the salvage mission, and even during the salvage mission, still there was no better than a 50-50 chance that the salvage effort would really bring the spacecraft back to life and be fully functional.
At that point, Hughes, being very creative, came up with an idea that, well, we could participate in the mission at a price, that we would agree to fund the salvage mission out of our total loss proceeds, and after you've had paid the total loss proceeds, and that we would negotiate an appropriate division of any revenues that might be earned if the salvage mission was successful.
Had the mission failed, or had the spacecraft not been salvaged, Hughes aircraft would have been out about $20 million on the mission, but we were willing to venture that.
We thought that was a very fair compromise. It put Hughes in the risk, and it really, in our view, the underwriters could lose nothing. Right now, the satellite was worth nothing. Nevertheless, the American market did not respond in a favorable way, so we sort of packed up our contract drafts, got on a plane, and we head off to London to meet with the Lloyd's Group, various people from the French underwriting community, and we explained the same two ideas that we had explained in New York.
The response of the London market was very favorable, and in a very short period of time did indeed come away with London's agreement, where we'd share the revenue if it was a success.
Well, we were pretty excited about that, and we came home, and that really was just the start, because we still had the entire American market. We felt that if we could get an agreement with the lead underwriter, then more than likely the smaller companies would follow suit. That seems to be sort of the pattern. So we worked with them, and actually it really didn't take that long.
Soon, with some modification as to how the revenues will be shared, an agreement is reached with the lead underwriter. And finally, one by one, agreements are signed with 13 out of the 14 underwriters. This proves to be enough to continue forward with mission salvage. The word that the salvage mission will proceed is welcome news to the engineers back in El Segundo. They now have the go-ahead to salvage F3 during mission 51I, scheduled to lift off in August. The challenge becomes the struggle against time.
There was a total of about 4 months to the launch of F4, where the mission would occur. And that really left us about 3 months to deliver hardware. And we're talking about designing, developing, testing, and delivering some rather sophisticated electronics in a very short period of time. And at that point, it seemed almost impossible, but it was worth a try.
Ordinarily, that sort of thing would have taken several years, at least 2 years in the normal NASA thing.
It took a lot of long hours and a lot of missed weekends. A lot of people probably never even noticed that there was a summer that year.
After much planning, a scenario for the salvage operation emerges. First, the astronauts will capture the slowly spinning spacecraft and secure it to the shuttle's remote arm. Next, 2 electronic boxes are to be attached. One will bypass the automatic sequencer. The other will turn on the command units and deploy the Omni antenna, enabling the spacecraft to receive ground commands. After attaching a solar heater on the nozzle of the rocket motor, the satellite will be manually redeployed. To make this complex scenario happen, a number of teams are already working independently toward the collective goal. In digital electronics, various groups are hard at work developing the electronic boxes.
There are a number of challenges involved with designing and building this hardware. The first was to make sure that we understood what the requirements were. The second item was to build a team of people that could dedicate themselves to meet the schedule requirements that we had. We also had to worry about the astronauts with their gloved hands, whether they would be able to manipulate the hardware, to throw the switches. Therefore, we had to make, as well, not only to throw the switches, but also make sure that they're not thrown accidentally.
But I think what really made it doable in everyone's mind was the tremendous amount of motivation that the individuals working on this task had. I mean, we were here basically 7 days a week, 10, 12 hours a day for for those 3 very critical months of the program.
In design integration, the team is assisting NASA in the development of training hardware and is designing the special wire harness.
And certainly that turned out to be probably the most challenging part of the assignment in coming up with harness designs that were EVA compatible so the astronaut could use them on orbit and do the operations that normally take a skilled technician here in the high bay.
To satisfy NASA's safety considerations, the propulsion department continues to study the effects of freezing and thawing on the propulsion systems.
So at that point then we went into a series of test programs where we actually froze simulated hydrazine systems up at our Placerita test facility and demonstrated that even though we could get internal valve failures, there were no external failure modes which could cause hazards on the liquid systems.
So based on our best estimates, we concluded that the probability was good that it was a sound system under the circumstances and would work when it was activated.
The thermal team labors to assess the temperature issues relevant to the spacecraft systems.
The thermal issues involved in really deciding what we could and couldn't do with the spacecraft were broken into 2 areas. One, primarily, what would the electronics, batteries, that type of spacecraft equipment survive? What temperatures might they be expected to achieve during low Earth orbit? And then secondly, and perhaps the most important consideration, what could we do with the solid PKM motor? That's a case where you have some 8,000 pounds of propellant with a passive thermal control system designed to last a few days in space, no heaters, no temperature sensors, so that not only do you not know how rapidly it's cooling down, but there is no mechanism to warm it up.
Twice during this intense 4-month period, the astronauts who are to perform the salvage come out to El Segundo to practice with the hardware. They become an integral part of the Hughes team.
And I think that really provided a great deal of motivation for our own people to know that these astronauts were human beings as well. They weren't superhuman, they weren't snobs. That they were normal people like we are and had the same goals that we had. So it's provided a great deal of motivation for our people.
Saturday, June 22nd. The first astronaut visit. Using prototype hardware, the crew simulates many of the tasks that they will be performing in space. Although this visit is very successful, it is not without its tense moments.
I remember nervous technicians, 2 little lady technicians being brought in whose their specialty was in making these electrical connections, and they were going to show us how to do it. And I think the first time I went to put one on, I didn't put it on right. I mean, you got to have a learning curve, right? You give a guy a little chance to learn, and it was off a little. I was getting a feel for it, and it was off. And I remember hearing all this noise behind me. No, 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 no. And I looked at Chuck Rubin, and we looked at these ladies, and we said, hey, you know, we can do this. You just got to give us a chance. I think by the end of the session, they were happy with us, and we were convinced and had convinced others that we could do it.
Despite Fisher's confidence, the engineers realize that in space, the task will not be quite as easy as this training session has shown.
The primary difficulty was those connectors were designed to be mated here on Earth, not with a bulky spacesuit with a heavy glove on. So initially what we did was try to gather all the expertise within Hughes that knew anything about tool designing and kind of brainstorm the problem. And we gradually narrowed it down to some choice concepts, and we finally refined those concepts into a simple tool that the astronauts could use on all the connectors.
In addition to the Hughes visits, the astronaut crew spends many hours in intensive training at Johnson Space Center in Houston. Their regimen includes hours of practice in the Wet F, a water tank which simulates the weightless environment of space.
In this case, we had this very large satellite that we couldn't fully submerge in the water, so we ended up devising with some schemes that they would float this. The divers were well trained, and we had a tremendous task to get all these things choreographed so that we could put this thing in the water, move it around to the areas we wanted, and go through all the various 16 or so different positions that this thing had to be placed in so that we could perform the operations. That was a real task.
The things we had to learn were the best way to do this, the best geometric configuration. Should we lean inboard or outboard? Can we do this without destroying the UHF antenna? Exactly how far can I reach? Do we need an extension to the screwdriver? A host of different questions.
We also had a couple of other devices. We made a large mass simulator, since this was going to involve moving large masses around. We made a big mock-up, just a big cylindrical mock-up with all of the same mass properties that we hung from the ceiling in another building and used as I guess just as a confidence builder that yes, you can spin this thing, you can move it around.
Astronaut Fisher also spends some extra time in the gymnasium to prepare for the physical demands of the mission.
And I knew I was going to get to do this thing. And if I couldn't do it, it wasn't going to be because I wasn't physically ready. I went over there, and I've done some weightlifting before, but I gained 25 pounds of honest muscle. I was up to about 180, 185 for a guy that's normally 160. I was real strong.
Monday, June 24th. The engineers at Hughes are confronted by a new dilemma, centered on the warming of the perigee kick motor.
I was concerned that in the time we were spending warming it up, we'd be doing it in the blind. There's a possibility of not heating it up enough, or there's a possibility of overheating it in places, and I thought that would be kind of dangerous.
Rosen suggests that temperature sensors and a small C-band transmitter can be built into the nozzle cover. This would allow engineers on the ground to monitor the warm-up of the solid rocket motor during passes over Earth stations and ensure that the subsequent motor firing could be performed at a desired temperature. It is a significant improvement, but one that could jeopardize the hardware delivery schedule. A new team is formed to build this hardware.
The baseline Leasat recovery program, if you will, had already been underway by a couple months. We were in a catch-up mode. We had roughly 5 weeks to come up with a system, not only just a design, but we had to characterize it, completely test it, and get through the gates of NASA. We had to be, space qualified materials. We had to pass all the safety gates that NASA requires for shuttle missions, and deliver a workable unit in 5 weeks.
Saturday, July 27th. The astronauts return to Hughes for a final checkout of the actual flight hardware.
We knew we had to have a fit check of everything that we did, and we didn't have the time to I guess, to go through the same type of engineering that we do on a lot of other things. So we figured that the best way we could do it was to build a part and take it out and fit it on another exact duplicate of the Leasat.
Most of the tools were pretty well developed, but we had the wonderful luxury of having a flight article. The F5 satellite was out there, and we had a chance to fit things on a satellite made from the same mold. And that was, I can't think of a single thing more important than the work we got to do on that satellite.
Thursday, August 1st. All the required hardware, including the C-band nozzle cover, now known as the Rosen pieplate, is ready for delivery to the Cape, right on schedule.
I remember hand-carrying some of it down to JSC myself. It was a great feeling of elation to have completed the hardware. I think everyone involved felt a great sense of accomplishment, but there was still a lot yet to be done.
Saturday, August 24th. Launch day.
The most beautiful thing I had ever seen to that point was the shuttle before launch. You can't imagine this scene. It's pitch black, and there's liquid oxygen has caused ice to form all over the pad. There are huge hunks of ice, and it looks like we had snowball fights up there, or waiting to get in. It's weird and eerie and frozen, and the shuttle's hissing like some dragon.
The crew is ready to go, but NASA scrubs the launch due to weather problems.
Our first launch attempt was an abort because of a thunderstorm, an electrical thunderstorm, which we weren't able to see, and so we were quite surprised that we had to abort.
We knew that there was some bad weather somewhere, and I could pull myself up and look out one window and see some rain offshore, but when we looked out the top windows above us, all we saw was blue sky. So we knew that everybody was being conservative, and that's the right thing to be. But it's very disappointing.
Sunday, August 25th, the next launch attempt. This time, a computer failure cancels the launch. Another agonizing delay as NASA's safety procedure calls for an automatic one-day postponement. The launch is rescheduled for Tuesday.
Unfortunately, Monday happened to be a beautiful day. It was clear and it was sunny, and we were all upset that we had missed the best day of all.
Tuesday, August 27th, launch attempt number 3.
And we all woke up on Tuesday morning and turned on the weather forecast, and it looked like a very bad day. The clouds were heavy. It was raining down at the Cape, and I know personally I felt very depressed that this was going to be the end of a very intense effort and a very depressing end. We didn't think we were going to launch that morning. I really, when we went out to the bird, we went out in rain slickers, and that of course is kind of a bad omen to begin with.
I don't believe that any of us thought we were going to go. It was a surprise to all of us. In fact, Mike Lounge and I were sound asleep on the floor of the orbiter about 20 minutes before.
I had one fear, one doubt, and one worry, and they were all the same. And that was that we would not get launched in time to make this repair.
Yet this time, NASA finds a hole in the clouds.
And all positions have given Flight Director Cohen a go for launch this morning.
4, 3, 2, 1, ignition and liftoff. Liftoff of A-51I and the commercial deploy and repair mission. It has cleared the tower.
Dodging thunderstorms all the way, Discovery lifts off in a pre-dawn blaze of glory. Mission salvage, the most novel mission in shuttle history, is a reality. Wednesday, August 28th. The crew focuses its attention on the critical deployment of Leasat F3. This Leasat was modified on the ground to make certain that a repeat of the F3 problem would not occur. The deployment is picture perfect.
Kind of hard to believe there's going to be someone hanging on to one of those things in a couple days.
Boy, it looks a lot bigger close up, I'll tell you.
It looks big enough from here on the TV screen.
The Omni antenna comes up right on schedule, and F4 heads on to geosynchronous orbit. It appears that all is well. Saturday, August 31st. For the second time in 1985, Discovery closes in on the dormant Leasat F3 spacecraft.
Houston Discovery, we got a tally-ho, and it's dead center in the coas.
Roger that. Sounds good. And let us know when you start using a TV camera. We might look over your shoulder with it.
I'll tell you, it was a beautiful sight, and it was coming right down the chute. Dick executed an absolutely perfect rendezvous. When I looked in the COAS and saw the first reflection of the satellite as we came around into the sun, boy, that little Hummer was sitting right there, right in the pipper, and stayed there all the way in. It was a perfect rendezvous.
It was a strange feeling because even though you knew it was happening, you're watching yourself with a third eye saying, you know, is this really happening? Are we really about to do it? Is this really it or just another water tank run? But I think that we were so well trained for it and had such confidence that we could do it that it was like a second nature to us. We were definitely ready.
But hardware problems are about to change the face of the mission. Discovery's remote manipulator system, the robot arm, has malfunctioned.
In the normal operation of the arm, you tell the computer, by way of hand controllers, what you want to happen at the end of the arm. It's like scratching your head. You think, well, I want to scratch my head, so I move my hand back. And the computer decides what that means in terms of moving each joint. With the failure we had, the computer couldn't do that job. And if you have certain failures, all you're left with is manually commanding these motors that control the joints, one motor at a time.
This would make the work go painfully slow and create the need for an additional EVA the following day. Undaunted, the astronauts press on. Van Hoften takes his place on the end of the RMS.
Since we had the arm problem, we had changed our scenario a little bit, which is really no problem, but I brought out the little safing device for the arming lever and brought it out and spun the satellite around, grabbed hold of it, was able to stop it in front of me. Again, this is without any of the bars attached to it.
Okay, it's safe. Okay, Houston, safing lever's in. Next problem is, what do I do with this motor?
After a 2-hour struggle that includes some unprecedented maneuvering of the shuttle by Commander Engel, Van Hoften attaches a capture bar and gains manual control of the spacecraft.
And this thing is real big and massive, and as Mike would move the arm, every time he'd move it, it would involve an acceleration and deceleration. He was moving it in the so-called single joint mode, which every time he'd throw a little switch, the thing would put in a pulse and it would move a little bit further. And I had to sit there and damp all these out. So it was a chore, but we did it real slowly and smoothly, and Mike got me down to where I could hand this thing to fish.
I was waiting there in the foot restraints on the starboard side of the payload bay, waiting for Ox to hand it down to me, where I could attach my holding bar, or fish bar as we called it.
We got it. Okay, good spot, Fish.
And from then on, my job was to try and hold it steady while they got the arm attached.
Due to the RMS problem, it takes Van Hoften over an hour to install the grapple fixture, leaving Fisher to hold the 15,000-pound satellite aloft for an entire orbit.
So Fisher now using the handling bar to hold the CENTCOM in place.
EVA status report for him, status report 37 minutes ago, and it was good.
Okay, thanks. And we got a good shot of Fish bench pressing about 7.5 tons, I guess.
Although the satellite has no actual weight in space, wrestling its mass proves to be a challenge.
I had nothing but a face full of satellite. I could see nothing else. I had some cues as to when it was level because my arms are the same length and I was parallel to the payload bay, perpendicular to it, so I could straighten my arms out and knew I was relatively close, but our clearances were small. So I had to depend on calls from the cabin as to whether or not I needed to pitch up or pitch down, yaw left, yaw right. And I mean, I knew I was in space, right? Every action has an equal and opposite reaction. Because remember, every action I put into the satellite is being transmitted down to the foot restraints, and they are whipping around like a puppy whipping a rat.
Finally, the grappling is completed.
Okay, it's on. Take me down. Hey, oh, now we can get to work, huh? Way to go, you guys. Yeah, now we'll get to work fixing it. All right. Looking good.
I think we all felt a real sigh of relief that we finally got this thing. And I think probably the key point is once we got it on the end of the manipulator, we felt like, hey, our work for today is probably done. We could come out here tomorrow and finish this up. But the key part of any of this was just getting hold of it and getting it in the bay.
Fisher now begins to install a series of inhibit devices to safe the satellite.
No, we're not home yet. That lady hasn't sung yet. That lady's right in front of us.
We had to place 2 pins into the safe and arm mechanisms to ensure that they could not rotate. There's a 90-degree rotation required for those things in order to enable firing. Any one of them rotating could fire the Minuteman motor. We had a mission rule. If we found them in the arm position, we were to back off and forget it.
Okay, the safe and arm lever here is at the safe position. Roger that.
Fisher now concentrates on the installation of the bypass unit.
Hey, found a big piece of gray tape from the Flashwater mission. I'll bring it back and give it to him as a souvenir. Stuck on the end of the satellite.
Okay.
Wouldn't you know it, we go into darkness just as I get to the position where I have to put on my first connector. Things are different at night. If you doubt that, take a softball at night and throw it up in the air and see how much faster it seems to come down, how much greater the closure rate before you catch it. And we have lights in each of our helmets, but still there's shadows and there's newness to it. And I put my first connector on, and I just didn't like the way it felt. You know, I didn't like the way it felt. So I said, I'm going to take it off. And I took it off again, and I looked, and I put it back on. And it felt the same to me, but I was just positive the thing was oriented right. And so I made the rest of the connections, and they were on fine. But it was something I'd forgotten about it. I knew it was there, but it's one thing I hadn't trained for.
Now comes a critical moment. The unit is plugged into the main power system of the satellite. When power is applied to the unit, it must trigger a light, indicating that the satellite's firing mechanism is still deactivated. Any other result would mean aborting the mission immediately. Fisher flips the switch. The light comes on, confirming that the spacecraft's batteries are operating and that the firing mechanism is disarmed.
And as soon as the sun came up, we saw the sun just come up over the horizon, that little green light went on, and I held the box up and showed it to all the guys in the cockpit because we knew that another big step had been taken.
Fisher turns the unit off. It will be reactivated just prior to its release from Discovery. The next critical task is to attach the remote power unit to the despun portion of the spacecraft.
And Hughes would like a brief rundown on the despun shelf, too. How's it look?
Well, so far so good from where I sit. It looks brand new. It looks just like the one we just launched.
That was the technically most difficult part of it, because because you had to avoid crushing the UHF antenna. This thing is just made out of a little coil of 10,000ths aluminum, or 10,000ths metal, I think it's aluminum, and essentially a honeycomb cardboard type structure that you could easily bash with your fist. And you don't have any feedback in the suit. If you turn like that and your pliss or backpack hits this thing, I mean, you could just tear it loose and you'd seldom feel it. So we'd worked very hard to avoid touching it.
In one of the most exciting moments for man in space, Fisher completes the connections and prepares to deploy the Omni antenna.
Okay, RDU relay enable to enable. Okay. 2 green lights. 2 green lights. Roger that. RDU relay enable off. Okay. Done. Okay, check the Omni antenna area clear back there, Hawks. Yeah, it's clear. Okay, Omni deploy fire. Omni fire. Here she comes. Looking good. Looking good, buddy. All right. Hot dog, look at that, Jack. Omni deploy off. Omni deploy coming off.
I said we never doubted this was going to work, but somehow when I threw the switch to deploy the Omni antenna, and the thing really came up. I mean, not only were we getting battery and continuity lights, but the antenna came up. It was just great. I mean, here I was standing on top of the shuttle. I was, passing over the Hawaiian Islands right above me. I was looking up, and there were the Hawaiian Islands. The antenna's coming up, and it's just a gorgeous view. And we were real excited.
It has been an extremely successful day, and at over 7 hours, the longest orbiting spacewalk ever. Most of the major salvage work is done, but the astronauts must wait one more day to complete the rescue.
Houston, we're going to take the spacecraft to the park position.
Okay, we copy. Looks like good work.
For the crew on the ground, it is still a tense time.
Overnight, when we had to wait through until the second EVA, you really don't rest, you don't really relax, because you're just trying to go over in your mind what the astronauts may be thinking of. You're trying to recount anything you can think of with the hardware, any peculiarities that would help. Everybody feels like they've got that little bit of information that would make this even more successful.
Meanwhile, in the orbiter, Van Hoften uses this break to get some valuable spin-up practice. Sunday, September 1st. Van Hoften and Fisher return to the cargo bay. Fisher installs the C-band nozzle cover that will not only heat the motor, but will keep the ground advised of the internal temperature every step of the way.
Oh, Mike, it looks so great.
We love to talk about the fact that this nozzle cover was more sophisticated and probably cost more than America's first satellite did.
With the nozzle cover installed, Fisher now removes the safing pins.
Okay, it came out easily and no problem.
This is Mission Control, the satellite being positioned for Mission Specialist Bill Fisher to set the timers on the spun bypass unit.
Finally, moving back to the side of the satellite, Fisher throws the switches that activate a 13-hour delay timer, inhibiting the SBU from processing any ground commands until the shuttle is a safe distance away. Having replaced the grapple fixture with the spin-up bar, Fisher and Van Hoften now work together, attempting to properly align the satellite into its deployment position. This proves to be another tough exercise for the astronauts.
That's me, I'm sorry. How's the Omni, Joe? The Omni's clear. Okay, let's land it up again, Fish. I won't even worry about that damn.
One of the difficulties you have with two people in suits working where you can't see each other and trying to maneuver this great big satellite around was a real challenge. As it was just, it was kind of a struggle. It's like two guys trying to push a piano up 3 flights of stairs.
See, I'd lifted weights, okay? And I knew in my heart that if it came to a muscle, I said, by God, I'm going to hold it where I think vertical is, and nobody's going to move it. And I think Ox was thinking that too, so we were tugging pretty hard against each other.
You know, it's kind of funny, and you'd laugh at it if you weren't struggling so hard. But once we got it up there, it turned out, I think it was easier to do it alone than it was with two guys. But I know it would be easier with two guys if we'd had the time to train for it.
With the initial alignment complete, Fisher removes his handling bar. Ox Van Hoften stands poised on the end of the RMS as Lounge moves him to the final deployment position. Van Hoften now finds himself in a struggle to maintain control of the satellite.
Yeah, I just want to tell you, if something ever happens and I'm about to lose it, I'm going to give it a heck of a push to roll it. Bail out.
Realizing that the maneuvering of the shuttle is making it difficult for Ox, NASA instructs Engel to fly in a free drift mode. This solves the problem.
Okay, I'm ready. Okay, the rates look real good. 3, 2, 1. Okay, buddy, good pressure, Ox. If you can get me in here, I may be able to get another handle on it. Oh, it's going aft. Okay, it's a good push.
Once I got one push on it, I realized that, hey, this is going to work really well. Came around again, and by then I was getting a little bit cocky, I guess, and I figured, hey, I can get this thing up to 10 RPM.
Watch out, get me down, get me down. Okay, stop right there, stop right there.
So the trick had to be a very coordinated effort of me pushing it, and then as soon as I'd let go, Joe would try to fly the shuttle back up and get me in a position to grab this bar when it came around again.
That's 1.5 RPM, Ox. Here's the punch more.
So it was a real coordination attempt to be able to do this. And we had a lot of people, there was bets on the ground. I know that people said that I'll get one push at it and we'll never see it again. We'll never get anywhere near it.
After a total of 5 pushes, he releases the satellite, spinning it up to a speed of 3 revolutions per minute.
Well, there that bad boy goes. I can still see the timers blinking.
That was a real emotional high for us. And every time I'd see it going around, I could see the lights still blinking on the timer, so we knew that it was still functioning, everything was looking good, and boy, we were just about as happy as we could be.
I was standing there with the best view in the house. I had a better view than Ox did. It was super. I took some pictures of it, but mainly I wanted to watch this baby go.
It's just a great feeling, and you can tell from the voice of Bill Fisher that even he was elated and extremely happy, and you could just hear it on his comments that he was making back to the ground.
I've said this many times since the mission. I said it during the mission, and I'll say it now. The actual mission was just like a water tank run. I'd done it so many times, I didn't feel nervous. We were trained to do it, and I think I knew from the minute I got that first connector on that we were going to do this and it was going to work.
The operation is a complete success, but the patient isn't out of the woods yet.
There were still a couple of final steps that had to be done. We still had to communicate with the satellite. We still had a 13-hour timer that had to run out, and it had to then perform, the box still had to perform the function of flipping some switches to activate the command system on the spun side. But even so, we were all just thrilled at the progress that had been made at that point.
Sunday, September 1st. It is 1 hour since Ox van Hoften has released F3. An anxious crew waits on the ground at the MCC, the Mission Control Center in El Segundo, to hear that the spacecraft has been acquired by one of the tracking stations at Guam and Norfolk.
The MGSs, or ground stations, both, I believe, were splendidly prepared at this point. Equipment-wise, we're in very good shape. And the personnel on each site had developed a rather good-natured rivalry. The rivalry began to heat up in that each site wanted to be the first to activate the spacecraft. It was a matter of pride for each facility.
By now, the spacecraft should be making its first daylight pass over the Guam Earth Station. This is the first opportunity for acquisition. The word comes back from Guam. They have the spacecraft.
From Austin, come CSR, this is spacecraft.
We have turn on.
We have turn on. We'll let you know when we have telemetry. Tell me when you got two.
We've seen both carriers. Okay.
Within 3 or 4 seconds of it coming into the sun, and the signal was, the command to turn the units on from the ground was right at sunrise, if you will. She came alive, and all of a sudden we had half a spacecraft. We could see what was happening on one side.
The initial telemetry, as it came alive and flickered onto the screen, we saw rows of question marks turn into numbers. And each one of those numbers would be an important piece of information for the rest of the mission.
And everything looked nominal, and by that I mean things were expected to be at freezing temperatures, the different shelf temperatures, and the spacecraft was indeed, I mean, alive for the first time. We could listen to it.
Later, when the 13-hour timer has elapsed, a command is sent to the spun side of the spacecraft. It is from here that the long-awaited data on spin rate, attitude, and temperature will come. Again, on the first possible pass, the command is received and the telemetry begins to flow.
Just on the first blush of the data that we were looking at out at the control consoles, spacecraft looked much warmer than we'd been expecting, or that had been predicted by thermal. And as far as all the subsystems, the integrity looked as if they'd been preserved.
The bulk temperature of the spacecraft is 30 degrees, well within the performance limits. But a major question is still unanswered. Data on the solid motor temperature should be coming on C-band, but Guam is having difficulties.
And initially, when the spacecraft was redeployed with the C-band transmitter on it, we weren't getting the C-band data. There were little glimpses of it, and we weren't sure what was happening at first.
Meanwhile, a meeting is held at the MCC to determine if it is safe to spin up F3. The concern is that the hydrazine propellant may be frozen.
It looked like about 30% of the hydrazine was solid, but because it was desirable to spin it up to get a more favorable control system operation, it was agreed that we would attempt to spin it up, and if in fact the lines were still frozen, we wouldn't get spin up and we'd stop.
The spin-up command is sent to the spacecraft. Fortunately, ice is not impeding fuel flow. 4 successful burns bring the spin rate up to an acceptable 24 revolutions per minute.
We found after we spun up the spacecraft that our sun angle was approximately 14 degrees off of where we'd expected. The aft pie plate, which is powered by solar cells, wasn't receiving any sunlight, wasn't outputting any C-band signal. It seemed to exonerate the ground segment, and the next phase would be for us to slightly reorient the spacecraft to start getting the C-band data and just find out what our PKM temperatures were.
Once the attitude was corrected, we were getting a good solid C-band signal from the spacecraft.
But data on the solid motor temperature is somewhat puzzling.
The temperatures that were coming back from the temp sensors indicated that the motor was a lot warmer than anyone had expected. We weren't sure how to interpret the data. The immediate thought was that maybe the data isn't reliable. We also felt that maybe the thermal analysis still had some upgrading to do. So we sent the thermal analysts back to do some more re-looking at their analysis to see if there might still be some areas that need more detailed modeling.
The model we had, while it was an order of magnitude more detailed than any model we'd used for prediction of performance during the development of the spacecraft normal operation, was still significantly inadequate for these long time cool downs. It was not giving us the right numbers.
After revision, it's clear that the data coming back is not only good news, it is reliable.
It appeared that the motor had been subjected to relatively benign temperatures, and that everyone felt the chances were very high that the motor would fire successfully.
With the thermal question answered, spirits are high. It's now just a matter of waiting as the motor warms to the optimum temperature for firing.
There was pressures to warm it up rapidly and perhaps fire it a little bit colder than it might otherwise be fired. But to wait for that period of time to 40 degrees Fahrenheit would mean that we'd run the risk of not delivering the satellite on time to the Navy and lose some money. So we spent a lot of time looking at the technical aspects of that. Finally decided we'd play it safe.
It was almost a watchword in the hallways and the elevators of S41 throughout the site of what's the PKM temperature today? It was as common a question as how's your wife doing? It became almost a watchword for us. All of it was preparatory to firing the PKM.
It is during this waiting period that Leasat F4 has arrived on station. After 2 days of normal testing, F4 experiences a mysterious power outage in its UHF payload. All efforts to revive the spacecraft fail.
It was a heartbreak, and again, you know, doing whatever you can. We turned things off, turned them back on, reconfigured all of the transmitters, reconfigured things that we didn't even feel could be the cause of the problem. We just did everything we could, and we realized that it looked like a failure in the output section of the spacecraft, downlink. So it was a real heartbreak.
It made F3 more important. The fact that F4 failed, which was a great disappointment to all of us and happened within a week of the success of the F3 encounter, made F3 that much more important to us.
F3 became not only still a baby for us to coddle until it was warm enough, but a very important asset, something that, not to say that we redoubled our care, because I believe we were as careful as we could be before, but it also highlighted to us the importance of having a viable F3 spacecraft.
In the ensuing weeks, data from F3 keeps streaming in to the Earth stations at Guam and Norfolk.
During the 2-month warm-up period, the ground stations were staffed to handle the F3 low Earth orbit passes on a continuous basis, 7 days a week. Each station would receive between 7 and 10 passes per day, each one of a very short duration. And this would occur at all hours of the day and night.
The temperature data indicates a very strong likelihood that the PKM will be ready to fire in late October. The wait would soon be over. Sunday, October 27th. Temperatures have risen and are stabilized at acceptable levels. All is in readiness to send the command that will fire the big perigee motor.
Good luck.
All the hard work of the last 6 months rests with this command. Either the engineering creativity will be verified with the underwriters enjoying the financial benefits, or F3 will be no more than a lost statistic in the history books. At exactly 8:53 a.m. Pacific Standard Time, Hughes notifies Guam to send the fire command sequence to Leasat F3.
9 seconds, first arm in advance. Command accepted. 0. And arm in advance.
Something's happening, spin rate is changing.
Okay, looks like we haven't fired. Guam, you see Doppler?
Yeah, it's changing too much to Dalcrest.
Plus 27 seconds.
We are firing.
It's good, let's keep it going, keep it going.
The motor has fired successfully. Leasat F3 is on its way to geosynchronous orbit. All systems are go.
Okay, we confirm stop firing. Everything looks nominal.
Okay, we have a real one. Norfolk, she's going to be coming by your way next. Guam, hell of a job.
All right.
Great team. Now, when do we go after F4? What is
The feeling at that moment was just absolutely enormous elation. We all jumped up out of our seats. We were all applauding. We knew that the repair had been extremely successful.
We had a near perfect orbit. It was just like picking up where we were supposed to be on April 13th. Only this was October 27th, and all the uncertainties and the hopes and frustrations in between. So we were on our way.
And the Navy was tickled to death because the satellite, after all, got into service, and at that, it got into service a day early. And not many space programs equal that record.
But I think the most important implications to us was we earned the respect and admiration of our customer in a way that we couldn't have if everything worked perfectly. Because they realized that these spacecraft are difficult to build and sometimes they don't work. But we didn't walk away from it. We actually stepped up to the problem and fixed it. And I feel good about that, and I think everybody at Hughes should feel good about that. And I think the Navy respects us for that.
Thursday, December 5th, 4 p.m. Pacific Standard Time. A fully functioning Leasat F3 is turned over to the U.S. Navy.
Among other things, it taught us a little humility. It was the first time we'd really lost a satellite because of our own fault since 1965, or 66, I guess it was. And so we all took a course in humility, and I think are better for it.
The insurance market is going to be a very, very valuable part of the space business in the years ahead. They're going to be a partner in the space business. I think they've gone through an educational process just as we have. We've learned more about their concerns. I think they've learned more about ours. Between the two of us, I think we've come out better.
It's unfortunate that these things have to be done, but anytime you're at the cutting edge of technology, manufacturing very sophisticated devices, there are going to be failures. And with these failures, it's if there is a vehicle or means to rectify them in orbit, not only is it visually exciting and very viscerally moving, but it's something that's very important to this country.
But there is no question that in this mission that the manned spacecraft program came to our aid, pulled our fat out of the fire, and the astronauts were clearly made of the right stuff. And we owe a lot to their dedication. They literally risked their lives to help salvage our satellite.
We've got a great team of people here at Hughes, and when you pull them all together and you've got a mission to accomplish and people are motivated, that you can do almost anything. And I think that what the team did here was really remarkable.
I think it's terribly important to capture something like this because 20 years from now people will say, you know, how did it go the first time? And now they'll know.